Okay, so I cut my own self off on that last piece of the video. So let's pick up with what I was saying. Here's our central limit theorem. And if you were to pick sample sizes that were 30 or bigger, and it's drawn from any population with a mean that we're going to call mu and a standard deviation that we're going to call sigma, then the sampling distribution, so it doesn't matter what, this is a picture, I guess, if you will, of what the population would look like, but the sampling distribution, if it's bigger than 30, always approximates a normal distribution. And the greater the sample size, the better the approximation. So if the population itself is normally distributed, then I think it makes sense that the sampling distribution would be normally distributed also, and it wouldn't matter what size n you have. So what does this mean for you? Well, the central limit theorem says that the mean of the sample means is mu, and the standard deviation for the sample means is sigma divided by the square root of n. That allows us to do problems like the following. So let's see. You can take a look at those pictures if you want to. I want to get to my problem. So we want to actually interpret this central limit theorem. So let's take a look at the example they have on slide 18. We have cell phone bills for a city that have a mean of $63 and a standard deviation of $11. We do a random sample of 100 bills, and we find the mean of the sample. Find the mean and the standard deviation for the sampling distribution, and then sketch. So let me see if I can write down everything that just said. So the mean is $63, and notice I'm writing the mean of the population. The standard deviation of the population is $11. We sampled 100 bills, and they want me to find the mean of the sample averages and the standard deviation for the samples. So this is if we go in and we randomly select 100 cell phone bills over and over and over and over again. What would the average of all those averages be? And it would just be $63. The standard deviation, however, is the standard deviation for the population adjusted by the sample size. So it has a much smaller standard deviation, and that would be 11 divided by 10, so $1.10. So they have the same mean, but the sample standard deviation for the sampling distribution is much smaller, which you can see on this next page. Okay, so then they say, well, how do we use the central limit theorem to talk about any of this? And it says the sample size is greater than 30, so then the sampling distribution can be approximated with the values that we found. And we can consider that the distribution, even though we don't know anything about the population, the distribution of all the samples is normal. I know this sounds like a bunch of jargon, and I guess it probably is. So let's see if we can look at another example, see how some of this is all related. The training heart rates of 20-year-old athletes is normally distributed. So we're told ahead of time that the population is normal. We're given a mean of 135 beats per minute and a standard deviation of 18. We're only doing random samples of size 4 this time. However, because the population is normal, then we know the sampling distribution will also be normal, and the sampling distribution of the sample mean is going to be mu of x bar will still be mu, so it'll be the 135, and the standard deviation for x bar will be the standard deviation divided by the square root of n. So the standard deviation will only be 9. So on the next page, they draw this, they show us the calculations, and then they draw it for us. So if you look, there's your mean, and then 1, 2 standard deviations away, and so forth. And that is not how they drew that. Well, I don't really appreciate them doing that. Anyway, I would have drawn it like this. If I was going to draw the sample mean, the 135 is here, and then 1, 2, 3 tick marks. I would have added 9 to each of these. So this is 144, this is 150. Yeah, I can't add. 53. What is wrong with my brain? And then 162. And you can go in the other direction by subtracting 9s. Okay. So they're making way bigger of a deal out of this than they probably need to. But it's to lead to the following. So if you want to talk about X bar in a problem, then the z-score is still going to be the value that you care about minus the mean, then divided by the standard deviation for what you care about. See? So they're calling it standard error because those are both the same thing. So let's try actually working a problem. Okay, so this next problem is actually the stuff that you've been doing in 5.1 through 5.3 already. And let's take a look at the wording, see if it helps. I have an education finance corporation that claims that the average credit card debt carried by undergraduates is normally distributed with a mean of $3,173 and a standard deviation of $1,120. Holy cow. Now, I heard the word normal, and I heard the word mean, and standard deviation. So I'm going to write myself a note. In number 1, it asks us what's the probability that a randomly selected graduate that is a card holder would have a balance less than $2,700. So we know from previous sections that that X needs to change to a Z. So we say what's the probability that Z is less than 2,700 minus 3,173 divided by the 1120. So we get a z-score of negative 0.42. Since this is less than, that's the area that's on our table. We look up this value on our table, and we get what? Roughly 0.3372. And this is the probability of randomly selecting one graduate that would have a credit card balance less than 2,700. So on the next page, they show us the work. On this next page, the question now becomes, what if you randomly select freaking 25 of these people? What's the probability that their mean credit card balance is less than 2,700? So let's look at how the notation changes and how the work changes. The probability isn't that X is less than 2,700 this time. It's that X bar is. Okay? And so in order to calculate the z-score for X bar, you still take the value you care about minus the mean divided by the standard deviation, but it's the standard deviation of X bar, okay? So the value you care about is the 2,700. The mean was 3,173, and the standard deviation was 1120. But the standard deviation of X bar is 1120 divided by the square root of 25. And so your z-score then is what? 2.11, which is way different than what we had before. I feel like that's wrong. Should be wrong. Hold please. Just kidding, it's negative 2.11. I lost my negative sign. Alright. So that's an even smaller z than what we had last time. So the probability is going to be smaller. And that makes sense, right? If you're going to randomly select one person versus 25 people, your probability should go down. So on the next page they show that they can do the same math as Miss May, and then they look up on their table and find a probability of 0.0174. So the probability went down greatly. The process is still exactly the same. The difference is right here, folks. Pay attention. This is like magic, but different. This division right here is different because you're talking about X bar instead. So if you have a question about a mean, then you just need to remember, oh yeah, I need to adjust it by using the square root of n. I'm going to wrap this video up, but I am going to do one more example on one more separate video. So that ends our slides. Have a great day.